I really appreciate you spending your time with us over here. Ventilation air has become one of those big topics. We've really seen it being pushed in Texas because they've jumped up to the 2015 codes. We're still in 2012 as we speak, and it's not being pushed as much, but there's still a lot of confusion. So let's be clear right off the bat. We talk about a lot of different types of air. The air that we're going to be talking about today is specifically going to be ventilation air, whether it's natural ventilation or mechanical ventilation. But it's going to be the air that we typically say that the house needs to breathe. That's the air that we're going to be talking about here today. There is combustion air that's a different type of air that we have to bring in for combustion burning appliances. We have makeup air, and that's that air that we're going to bring in for making up what we're exhausting from kitchen hoods, that type of stuff. So there's a lot of different types of air that we deal with and have to bring in. But for the most part today, specifically, we're going to be speaking of the ventilation air and those codes that work around that. A lot of confusion, a lot of misunderstanding. So whether we get it exactly right or not, you guys are going to just have to understand we're opening up conversations. There's some of it's open to interpretation, and whenever you leave anything open to interpretation, there's always arguments. So I'm very glad to see that we have some code officials here with us today to be able to give us their perspective on what it is that they're going to be enforcing in your marketplaces. Everybody good with that? Good. We're going to have one break here in the middle of the program, right before I get into the psychrometrics part. But for now, let's go ahead and get started. It's an interactive class. I want you to talk back to me because 3 hours of listening to me, you guys are going to be quite tired. So let's get that interaction coming back to me. All right, tight construction homes. Man, when we start building our homes like a Yeti ice chest, the way that we condition that home is going to have to change. We can't do the same thing we've done in the past. You start living inside of a Yeti, it starts getting nasty pretty quick if we don't do our jobs properly. We're in the HVAC business, is that right? Heating, ventilation, and air conditioning. How often have we been doing that ventilation part, the V part of HVAC? We haven't been doing a good job with that part. I just want you guys to understand that. So if we're not doing the V part of the HVAC, that means we're just hacks. Oh no, we're not hacks. We're not. That's not what we're going to do. But here, let's think about what we're going to do here. If you go out fishing and you come home, you take the fish out of the ice chest, you rinse out the ice chest, close it up, and put it up on a shelf. After about a month, what's that ice chest going to be like on the inside? Mold, mildew, oh yeah, I've got all kind of stuff. But if you take a towel and strategically fold it in half, then fold it in half again, and lay it on the edge of that ice chest, close the lid, and leave that gap around the top, that ventilation in that ice chest. What's going to happen in that ice chest now? It's going to dry out. So what you're telling me is that the mold and the mildew happen from the moisture on the inside of our Yeti. Is that right? Not so much the outside, which we're more concerned about in our previous lives. Now it's the moisture on the inside that's trapped that we need to be able to take care of. So you figured that out over time, that if I fold it and fold it again and fold it maybe one more time, that I have a certain amount of ventilation air that's required to keep that from molding and mildewing. Is that right? What if, because somebody has taken that time to identify exactly how much air you need, what happens if you take that information and you bring it over here to Brian? You say, Brian, all you have to do is put a towel on the top of the ice chest, and man, everything's going to go away. So Brian says, okay, great. He takes a paper towel, lays it on top of the edge of his ice chest, and closes it down. What's going to happen inside Brian's ice chest? Oh, so it's not just necessarily you have to have a towel there, you have to have a towel with a certain thickness. So I have to bring in a certain quantity to be able to stop that moisture. Is that right? What if they said, Brian, all you have to do is put a towel there. And you say, okay, I put a towel there. All right, I did. I take it out, I close it back up and put it back up there. What's going to happen, Brian? It's going to mold again. So a certain amount of time is going to have to pass where I leave that there, where I get a certain quantity over a certain amount of time. And how long is that time frame that I need to leave that towel there, Brian? Pretty much continuously in our marketplace. Is that right? I start closing that thing down, it's going to start getting nasty inside there. So continuous seems to be a key word that we're going to have to pay attention to as we move forward. So a certain quantity, and we can't vary for. What if I just took half of that? Instead of folding it twice, I only folded it one time. Is it going to mold in there? Maybe. Maybe it will. I don't really know. And that's the key. Anytime we back off from what somebody's already scheduled and said, we've researched it, this is exactly how much you need, and we start backing off from there, is it going to mold? We don't know. Depends on how much moisture they produce inside the house. Is that right? And we might not know that for 3, 4, 5 years. Interesting. After a month in tight construction, things start changing inside that home. It's going to start getting nasty inside there. And what we're seeing is it's 3, 4, 5 years down the road, and everything's starting to really get ugly. That's well past the inspection. But it's interesting about our codes because they go through a code process where we say, okay, well, it's going to go to the LSU CCC, so it goes to them, and then it becomes law. So even 5 years down the road, they go back and say, oh, did you do what the code said? And he said, well, no, the inspectors don't inspect that in our marketplace. Well, the state of Louisiana, it became a law that all of those codes come into place, so the liability starts showing up. So be aware of that. Grandma's home? We didn't have to worry about Grandma's home. Man, it was so leaky, we had 1 to 2 air changes every hour in Grandma's home. Man, you could stand on the south side of Grandma's house and feel the north wind blowing. It was great. How did we heat Grandma's home? Gas, with 4 furnaces everywhere, is that right? We had those little space heaters everywhere. Where were they vented? Right there into the house. Did we worry about carbon monoxide? Oh, no carbon monoxide issues there because the house leaked so much, we just changed over the air. As fast as the carbon monoxide went in, it went out again. Not a problem. That was easy. But then the energy crisis came in the 70s and said, oh, we've got to start tightening up these homes. We can't have them as leaky as we used to. So we started putting plywood on the outside. If I could slow down the airflow into that house, I could slow down the moisture rate, I could slow down the heat transfer rate. And instead of it being 2 air changes an hour, now we were down to 0.75 air changes an hour. Now stop and think about that. 0.75 air changes an hour, that's still 3/4 of the air inside that house leaking in and out of that house every hour. That's still a leaky house, isn't it? Typical home of today, we're down to about 0.35 air changes an hour. About 1/3 of an air change an hour inside that home just leaks in and out. That's what we call the house breathing. That's nice. You start getting into extra tight homes or foam homes, that type of a home, we're down to about 0.1 air change. Down to about 1/10 of an air change an hour inside that home. We're getting tight. Now, I'm a Cajun and I'm not a smart man, so I had to kind of put these numbers together and kind of figure out what does this really mean to me. So I built one house, 2,000 square foot, 10-foot ceiling. With one home, that's 20,000 cubic feet inside that house. If Grandma's home leaked 2 air changes an hour, that's 40,000 cubic feet an hour. Divide that by 60 minutes in an hour, that's 660 CFM. That's a 1.5 ton blower in Grandma's window blowing 24 hours a day, 365. Is it any wonder we had to put a 3-ton window unit in that little 800 square foot home just to take care of the living area? I mean, we had to oversize air conditioning dramatically just to be. So the only way we're going to be able to change that would be to identify with a blower door test, and we're going to cover that here in just a few minutes, okay? Cool. Thank you. So how can I change that natural ventilation rate? Well, wind can change that. If I have a prevailing wind from somewhere and it's blowing against a stick construction home, it might leak through those sill plates anywhere that he's talking about, the windows, around those doors, all of those places, because the wind's pushing on there. What you got to get in your heads, guys, is for every 1 CFM that goes into that house, 1 CFM goes out. Does that make sense? For every 1 CFM that goes out, 1 CFM has to come in. Remember that. Because that's what's going to be huge. As we start tightening up these homes, what happens to the size of the air conditioning system? It goes down. Our tolerances are getting less and less and less. We don't have that extra tonnage to be able to take care of stuff anymore. It's going to get more and more critical. The wind, as I'm blowing that in, it's pushing it out. So it's going to increase that leak rate. Does that make sense? Good. Exhaust fans. If I start turning on the bath fan, there's 50, 80 CFM. Is that right? If I have 50, 80 CFM going out, that means I have 50, 80 CFM coming in. Okay, let's turn on can lights, especially on the 2nd or 3rd floor. Heat travels from hot to cold, absolutely. As that heat rises up to that 2nd or 3rd floor, it's going to run right through those can lights. You know the can lights I'm talking about. You standing up in the attic space, you're looking at the can light, what do you see? You see the floor, absolutely you do. You can get about 30 CFM through a can light. How many can lights they have in some of these homes? You're getting it. Tons and tons of them. Good. Attic accesses, you know how leaky those are? Heat traveling hot to cold. Moisture traveling wet to dry. It's pushing everywhere. The dryer, something that's not thought about very often, but it's huge. How many of you guys got kids at home? When does the dryer shut off? Never. Okay. So if it's not shutting off, that's 200 CFM being exhausted out of the house. If I have 200 CFM being exhausted out of the house, that means I have 200 CFM. That's hot, dirty, humid air. Does that make sense? The home naturally breathing. The home naturally breathing, we just said, was 100 CFM. Now you turned on your dryer and you doubled the amount of moisture being brought into that house. Does everybody get that? Cool. Hood vents. We're getting bigger on the hood vents? Yeah, what are we seeing out there now? Commercial grade hood vents, right? 800, 1200, 1600, 1800. I heard yesterday was the big one that I hadn't heard of yet. But they're putting all of these huge. So if I have 1600 CFM going out, that means I have 1600 coming in. Hot, dirty, humid air, absolutely.
Well, it's wishful thinking because most of the time they don't have anywhere near that much coming in.
Good. So where is it coming in from? Because if it's exhausting out, it's got to be coming in. So it might not be coming in from the makeup air where it's supposed to be coming in. Where's it coming in from? Windows, doors, cracks, crevices, everything. And that's where the problem comes in. That's where the problem starts coming in with the mold and mildew, and I'm going to show you guys that here today. Pressure imbalances can come from the ductwork. This is where it all started. Independent studies have showed 25% duct leakage is typical around. We found 20 to 40% typical down the East Coast, West Coast. It was just phenomenal, the amount. If I have a 2-ton system and it has 4 ducts, one of them completely disconnected is 25% duct loss. We wouldn't stand for this if we walked into the attic and saw this. But because they're all small holes everywhere, we've been letting it go for years. So 200 CFM blowing up into the attic, means I have 600 coming in the house, 800 leaving the home. If I have more leaving the home than I have coming in, the home goes into a negative pressure. The home sucks, absolutely. So if we have this situation, the fix is to put the 800 CFM in and take the 800 out, because our air conditioner doesn't make air, it just circulates the same air over and over again. If we had this same situation on the return side, let's say I have 100 CFM of leakage around an or drive joint, I'll take 100 for there, I'm only going to take 700 out of the house. If 7 comes out of the house and 8 goes in, the whole home goes slightly positive. So if it's going positive, it may be good, it may be better, but I have to be very careful of where I take my makeup air from, or my ventilation air from. I don't want to take it from a 140-degree attic. Does that make sense? Good. Which one would produce dust inside the home? A negative pressure home or a positive pressure home? I'm positive it's both. Because if I'm bringing it into a positive, I'm sucking the dust in from this spot. Is that right? If I'm in a negative, where am I sucking the dust in from? Both are going to produce dust. The air conditioner doesn't produce dust. It just, when they shut those doors, the air conditioner blowing into that room now makes that room go into a positive pressure. If that room goes positive, it's going to start forcing the air out through those can lights, through the cracks in the walls, floors, ceiling, everywhere. It's going to force air out. If I'm forcing air out on this side, what's happening on this side of the house? The whole home just went negative. So the entire home is now sucking moisture in and heat and dirt from the rest of that house. Where do we say we're going to get the air from? We always say, oh, we close the door, so where are we going to get the air back to the return from? Under the door, yeah, right? Yes, sir.
So that positive pressure is like when, like I know in my home, if I close the door and one's almost like slightly closed, it's going to close.
Absolutely. That's the pressure imbalances. Because now, if I slightly close that door and I'm pressurizing that room, what's it going to do to that door? Right? It's going to close that door. You got it? Good. So now you can hear it going under the door, right? You know why it whistles? Because it doesn't know the words. Quit that. Quit that. All right, so we got a pressurized room. So if it's going under the door there, it's going through the can lights, it's going out the windows, it's going everywhere but back to that return. Whatever I lose on this side of the house, I'm going to suck in from that side of the house. So you start talking to the homeowner because they're telling you, oh, my air conditioner doesn't keep up. It feels sticky, it's hot, it's nasty. And you say, do you close any of the doors? What are they going to tell you? Oh, I don't close the door. I don't close the doors. So you go and do some investigating. And I want you to pay attention to that, because if you just look at the door frame, and you start seeing dust in that door frame, it tells you that that door has been closed. Does that make sense? So you ask them about it, and you say, hey, I noticed that I see some dust here, so that means that door has been closed kind of during operation. Do you normally close the door? Oh, yeah, we do close it, but only at night. Oh, yeah, only at night. How long is night? It's like half the day, right? I mean, that's the deal. So half the day, I am pushing the bought and paid for air out of the house on this side, and I'm sucking in hot, dirty, humid air on this side of the house. It's no wonder that the air conditioner is not keeping up. Everybody follow that? Cool. So here's the big room that normally happens in. It's the master bedroom. Because I call that, Christmas. You know, the once a year that you get to go in and open up the presents? You know what I'm talking about? Okay. So you want to have a little bit of privacy, so you close that door. But now it's not just 200 CFM going in there. Now I got the 200 for the master bedroom, I got 100 for a closet, 100 for the bathroom. I've got 400 CFM, and we said that we're going to have it go underneath the door. Is that right? So we cut the door. And the industry standard is what? 1 inch. Yeah, we cut off 1 inch off of the bottom of the door. I need you guys to understand that 1 inch is definitely not enough. You know that it's not enough. But if it's not enough, how much is enough? For every inch you cut off, you're going to get 4 CFM. Real easy to remember. 1, 2, 3, 4 CFM for every square inch. Everybody good with that? So if I have 4 inches for every square inch, 36-inch door times 4 CFM is 144 CFM. Everybody good with that? If I have 144 that I can get through there, but I have 400 going in, what happened to the other 260? It all got blown out on this side. If it's all blown out on this side, what's happening on this side of the house? It all went negative. Is everybody getting that? Sucking it in through every crack and crevice on this side of that house. Every fireplace that we have comes with a combustion air. The code says that if you have a masonry fireplace or a manufactured fireplace, you should provide that combustion air. Now we've got a big old roaring fire, and you guys know that it takes a lot of air for that big roaring fire. Do you think I can get anywhere near that much air through a 4-inch duct? No. So the problem is we're putting in the duct, but on every one of those manufactured fireplaces, you know what there's an option of? A little blower. A blower that provides combustion air that you put right here. You know what's never installed? The blower. So I can get enough combustion air if I put the blower there, but I can't get enough combustion air if I'm just trying to bring it in there. So in the other part of that is in the state of Louisiana, we are not required to put in the glass front anymore. So the code said it, we changed the code so you don't have to have the glass front. So if I don't have a glass front and I don't get enough air for combustion through the 4-inch, where am I getting the combustion air from? It's sucking combustion air. As it's sucking that combustion air into the fire, where is all that air going that I just heated up for combustion? Right out the flue. Is everybody getting that? So if I have all of that air going up the flue, what's happening on the rest of that house? All right, so ventilation. We talked about Grandma's home. We talked about that being uncontrolled and natural ventilation coming in from everywhere in Grandma's home. As we tighten up our homes, whether it's foam or just tight construction, we're going to have to start bringing it in controlled. We're going to not have the house breathe on its own anymore. We're going to have to put it on a respirator. And we're going to control the amount of air going into our homes. Bring it in controlled. Now, you have to bring in mechanical ventilation when it starts getting less than 3 air changes an hour in the state of Louisiana. So, well, wait a second, 3 air changes an hour. Grandma's home was 2. When we start talking about air changes an hour now in the codes, they are talking about using a blower door on the house. So if I take a blower door and set it in that exterior door and start sucking the home into a negative pressure, if I had a 0.35 air change an hour home, naturally just leaking in and out, 1/3 air change every hour, and I suck it into a 50 pascal, 0.2 inches of negative pressure vacuum, what's going to happen to the leak rate? It's going to go up. It's going to leak faster. Does that make sense? So that 0.35 air change an hour home might be 7 air change an hour under 50 pascals of negative pressure, under a vacuum. Does everybody get that? Good. So when we're talking about tight homes and checking that out, it's talking about with a blower door test being done, an envelope test being done, and under that negative pressure. So that 7 air changes an hour might equate kind of close to somewhere around that 0.35 air changes of natural ventilation. But the ventilation in that home, we have to have it. The foam home, the air inside there is full of VOCs. Even in tight construction, VOCs, volatile organic compounds, the carpets, the paints, the glues, the the particle board on our tables, the chemicals you bring in with your dry cleaning. All of those chemicals are being released inside your home for years. Now, as it's being released in there, just understand that your air conditioner is not making air, it's turning the same air over and over again. If the chemicals are in there, what are you going to be breathing? Those chemicals. The chemicals we use to clean. Climb inside of a Yeti and say, well, I clean the house on a regular basis. Climb inside of a Yeti, close it up, and start spraying the chemicals you use to clean. That's what you've just done with the tighter homes. We have to get past that mindset of those loose homes that we've been living in and been doing construction in, because now we're tightening them up. People up north have figured this out a long time ago. We're just starting to see it now. Please, please be careful as we go forward. We have to ventilate that home. The off-gassing of these things continued for years. And it's faster in hot environments and humid environments. Where do you guys live? Hot and humid. So it's going to off-gas very quickly, and it's going to start pushing all of these chemicals inside the house. And it's maybe not necessarily just harmful to you, but it's harmful to the equipment in that home as well. Anybody seeing any of the cans starting to rust out in the attic spaces in some of those foam constructed homes? Oh yeah. So anywhere that it reaches dew point, anywhere that I can get that air leakage down where it's starting to get a little bit of dampness to it, what's happening is the chlorides that are in the home, whether from the chemicals they're using to clean the house, or chlorides that are off-gassing from the VOCs, are going throughout the house. Wherever it reaches dew point, it's rusting. When does your coil not reach dew point in Louisiana? It's always wet. We're running into coils. You're getting 4 and 5 and 6 coils in a 5-year period. It's not the coil, because you're using the same coil next door in a ventilated home, and you're not seeing the problems. As soon as we start seeing those chlorides starting to come into play. So the chloride's in the air, and then it mixes with the moisture, and it becomes chlorine. And the chlorine is now causing the rusting happening. Nobody's ever seen this happen with the breakers, have we? Yeah, because it's reaching dew point. I'm sorry? On the hole, or right there on that grommet where the electrical's coming in. Right? Absolutely. It's got to be sealed up. Is that right? Got to be sealed. Because otherwise I'm bringing in the moist air, and it's coming right into this cold environment. We're lowered the temperature, reaching dew point, and the chlorine is just tearing up this equipment. What is it? It has to have the moisture in order for it to start doing damage. What is your body made of? A lot of moisture. So start thinking that one through as we start going forward. I'm thinking that probably you need to start adding ventilation air, and a certain quantity. And how often? Continuous. Yeah, I think continuous. Listen, ventilation, dilution air. Dilution is the solution for the indoor pollution. You like that? I made that up. I did. You like that? Yeah. Dilution air. It's the solution for the indoor pollution. It's the stuff that we have to have. Does it say? Okay, you got Grandpa in the ice chest, right? You got him in the ice chest, and you say, okay, well, I'm going to have dilution air in there a little bit. Maybe I'm going to fold the towel just right so he can have enough air so that he's not going to start dying inside there, right? We're going to have enough dilution air in there. But then you come along and say, well, he doesn't need it there all the time, so we're going to back it off to just a little bit in there. And then when he starts getting sick, then we're going to open it back up again and give him some more, right? We'll get him a little bit more. Or we say, oh, we'll just close the lid off, because we don't like to have all that humid air coming in to see Grandpa. Am I getting this? Somebody much smarter than you and I decided this is exactly how much ventilation air you need in this size house in order to be able to keep that home from molding and mildewing and keeping the carbon dioxide levels down and being able to keep the carbon monoxide levels from picking up. Does that make sense? Somebody much smarter than us. They wrote it down in the codes from the 2009, 2012, and now the 2015 codes. We're still following the 2012s in here and some of the stuff from 2009. So we'll talk about that here. In 2015 and the 2012, they say this. The building or dwelling unit shall be tested and verified as having an air leakage rate of not exceeding 5 air changes an hour in climate zones 1 and 2. So climate zone 1 is down in Miami. We don't worry about that. 2, okay, that's the vast majority of where we're at. So we can't have any more than 5 air changes an hour. Upstate Louisiana, it says 3 air changes per hour in climate zones 3 through 8. So that's 3 through 8. What we've decided here in Louisiana is we're going to put the entire state under climate zone 2. So we fall now under that 5 air change an hour maximum. That's where we should be. Maximum leakage rate of 5 air changes an hour. But we step back to 2009. And under 2009, we're allowed 7 air changes an hour. So we said, okay, we're going to still be able to build the house leaky. Under the 2009 here in the state of Louisiana, we don't have to verify, tested and verified. All we have to do is have the inspectors do a walkthrough and say, yep, it looks tight. Now, in order for them to do that job properly, they need to be on the job site about 7 times during the installation of that stuff. So it's tough for them to do that, but that's part of the code. That's what they're allowed. They either do a blower door or this walkthrough inspection. So we would like to see, from our perspective, we would like to see that a blower door be done on every new construction home. Why? Because you're doing a manual J saying the house is going to be this leaky. I know that it's going to be 7 air changes an hour maximum in this house, so I'm going to do my manual J on the front end and size my house, size my air conditioning to my home. But if they don't do a blower door test, they could be in at 9, 10 air changes an hour, as he told you. Is that right? It could be leakier, or it could be tighter. So we don't know what our leak rate on that house is. So we don't know what size air conditioner we need to put in. Does that make sense to you guys? Cool. So we're trying to say, let's please put a blower door on every new construction home so that we can set it and everybody knows what we're dealing with. So then it says, if you're doing a blower door test on the home, and Louisiana changed it from 5 to 3, and the air infiltration rate is less than 3 air changes an hour, you have to provide mechanical ventilation. So a typical foam constructed home would fall out at about 1 air change an hour. So you would think that every foam constructed home would require mechanical ventilation on that home. Does that make sense? Doesn't necessarily fall that way, but that's what you would expect it to be. So if we're getting into those tighter homes and it falls out at less than 3 air changes an hour, you're required to. But you don't ever know that until after the job is well under the way. So this is all discussion that needs to happen on the front end. I'm going to provide mechanical ventilation because I believe you guys are going to build a tight construction home and it's going to be less than 3 air changes an hour. I need to provide that ventilation air. Because if I don't provide that ventilation air and that lid stays closed on that home, what's going to happen inside? Mold and mildew, right? You got it?
And see, that's the biggest problem we have.
Got it.
Is going into a house, you don't know if it's foam, you're doing a rough-in on it, you have no clue until you go back until the final to find out that the whole damn house is turned into an ice chest, but they're only bringing in 4 inches of outside air, and there is no mechanical ventilation in the house except for a fart fan, a dryer, the kitchen hood, a fireplace. That's the only ventilation you have in this home.
Got it.
And it's getting even worse because now they're putting exhaust fans in the laundry rooms with dryers, so all your conditioned air you dump in this laundry room is getting sucked out plus the rest of the house onto the door because there's not enough air coming in order to supply an exhaust fan and a dryer.
Okay.
Same problem with us too, because you go sell them air conditioning and they change the phone.
Right.
You're already stuck in it. You got to sign a contract, so you have a problem.
Now we're all understanding. So that's what I'm saying. The more we can have this conversation, the more we can start adapting these codes to whatever it is that we know is right in our marketplace. Because these codes are written not for South Louisiana, they're written for the United States.
Right. Well, the biggest problem we have too is, I mean, you go to sell the two-stage system, you know, doing phone, and then they can't afford air conditioning because they got to do the Viking stove and everything grand, so then they put a single-stage system in, and it's even worse after that.
Okay, so we have some options. What is the problem with a single-stage air conditioning system in a foam-constructed home? It doesn't get enough run time.
And humidity stays.
Ah, okay, so we need something to be able to remove humidity. We're going to talk. We're going to talk.
Yeah, that's why we talk, because
That's
blows my budget out.
good. So we're going to talk. We're going to talk all about. We're going to talk about all the options we have going forward, guys. We are. So the code is what? Code is the minimum
Right.
that we have to do, right?
This is an insurance.
Correct.
The code is the minimum, and air conditioning contractors are responsible for all mold, mildew, and everything that ever happens inside of somebody's house. Is that right?
Correct.
Yeah.
Right.
It's always us because we got the biggest insurance policies, right? That's how it works. So understanding how to prevent it, how to talk about it, and how to get codes actually amended is your responsibility. So we need to be able to get you guys all talking the same talk. All right? So the blower door, it's called the envelope test. We're going to take the exterior of that home and seal it up as tightly as we possibly can. We're going to suck that air out down to 50 pascals of negative pressure or 0.2 inches of water column. And when I do that, if I'm sucking air out, that means I must have leakage coming in. Is everybody okay with that? So the more leakage I have coming in, the more I'm going to suck out. It's just how it works. All right, so if I find out that that home is 7 air changes an hour, 5 air changes an hour, what if it's only 3 air changes an hour? What am I now required to do? I have to bring in a mechanical ventilation system. Absolutely. I like using thermal imagery. I like using thermal imagery because if I could go ahead and suck that home into a negative pressure, I can start looking to find out where that infiltration is happening. In this particular case, it must be winter outside because it's sucking in cold air through the light sockets. It's pulling in cold air through the window frame, around the window sash, everything there, up around the top of that window, up near the ceiling. You're seeing it's being brought in there as well. So by using thermal imagery, I know where the heat is either coming in or leaving, and at the same time, I'm also able to figure out if heat's coming in, dust is coming in, and moisture is coming in as well. Is everybody getting that? Cool. I love this slide. This slide basically tells me what's happening in South Louisiana. Exterior, I have a 74-degree dew point temperature. Do we have dew point temperatures at 74? Pretty much all year long. Yeah, all summer long we have 74 dew points. Inside temperature, 75 degrees, 50% relative humidity. 1 4x8 sheet of sheetrock, under those conditions, I can produce 1.5 pints of water through diffusion through that sheetrock. But I cut 1-inch hole. 1 inch, 1 inch, 1 inch, 1 inch on that sheetrock, and that 1.5 pints of water turns into 14 pints of water. How many 1-inch holes do we cut in our sheetrock? Okay, so let's compound that. Now, you have these 1-inch holes everywhere in your house, and let's make that house go negative. What happened to that 14 pints of water? It went up dramatically. Is everybody getting that? What did we do to the size of our air conditioner on our newer homes?
Went down.
The moisture removing capability has been reduced, but the moisture that we're fighting now is inside that house. Is everybody getting that? So here's the rules. And the problem with the rules is people typically only read the first one and then they run away. So here's the dig. The first one says system design. It says outdoor air ducts connected to the return side of an air handler shall be considered to provide supply ventilation. Okay, so it's saying if you just take a duct and tie it to the outside and to the return, you're good to go, right? If you stop there, that's what we're seeing out there in our industry. Problem is you have to read the next two codes. The next ones say you have to have controls that enable a manual override and a method of airflow adjustment. So we have to have a damper in there to control it from 60 to 80 to 90 CFM, manual adjustment, and we have to have controls that can turn it on and override it. Does that make sense? Okay. The next one is the more important one. The next one that's more important says provide outdoor air at a, what does it say? Continuous rate. What does continuous rate mean? When does continuous rate turn off? See, that's what we read up here when the air conditioner shuts off, ventilation shuts off. Down here it says it doesn't shut off. Continuous ventilation. Now, that would be like saying, oh, okay, well, we can get ventilation when we want to. So we'll open the lid for Grandpa for a little while, but then when we feel like we want to shut it down, we'll just shut it down. I mean, we'll wait for him to get sick, and then we'll open it back up again. Is that making sense? That's what we said in the state of Louisiana because we added this. Instead of shall provide, we added shall be able to. Shall be able to. When we shall be able to, that means you have to put in a ventilation system to be able to have that air for Grandpa, but you can turn it on and off whenever you feel like it. You have to provide that. Who's going to turn it off and take responsibility for Grandpa? But that's what the state's telling us we can do now. So I just need you guys to understand what be able to was added so that we wouldn't be bringing in all that humidity, because if you bring in humidity, what else do you have to put in? So do you think somebody was concerned about how much it's going to cost to build that house, or they put this in? Okay, so I'm fighting that right now at LSUCCC. All right, so does everybody understand what the codes are actually saying here? The problem is we've been just taking that duct and slapped it on the return side of that system. When the unit cycled on, we brought in fresh air. What did we do to the runtime of those units when I tightened up the home and now have less requirements for air conditioning? What did I do to the shoulder seasons on? I don't have the runtime during the shoulder seasons I had before, is that right? So if I don't have the runtime of the shoulder seasons, I don't have the ventilation happening. Does that make sense? Are we still producing humidity inside the house? That's, it really is. It really is. And so that's why we're having these conversations.
Because if you keep a dehumidifier running 365, you're still pushing CFM into the house without it coming out.
But I have to.
Right.
But I have to. Is it coming out? If I bring in air through a dehumidifier or through some sort of a ventilation system, if I'm bringing air into that house, is it going out? Yes. Yeah. Is it? It's going out through the dryer vent.
Right, when you exhaust.
Right. It's going out through the bathroom vents. Going out through. Absolutely. So as I pressurize that house, going to a positive pressure, it's still going to find its way out. Every CFM that I bring in goes out. Yes. Cool. All right. So how much? The code says go to M15073. M15073 says if I had a 2,000 square foot home and it has 3 bedrooms, I'm required to bring in 60 CFM. Now remember what I said about that typical home, that 0.35 air changes an hour was about how many CFM of breathing? About 100 CFM. Remember that? I said a typical home breathes about 100 CFM. So what we were comfortable with it breathing 100 CFM, now we're saying, oh, okay, but if we bring it in through a controlled source, we're down to 60 CFM. So we're not bringing in as much as we had leaking before. If I had a 4,000 square foot home with 4 bedrooms, I'm looking at 90 CFM. Is everybody okay with that? Good, all right. So that's telling us exactly how much we have to have. It's telling us exactly how many folds I have to have in that towel to have just enough air to keep that mold from growing inside there. And when does it shut off? It's continuous. It's continuous. There is a contingency fee here. What it's saying here is that if you wanted to be able to cycle it off and back on, you can. Instead of having it on continuous, you can have it on for 30 minutes, off for 30 minutes. On for 30 minutes, off for 30 minutes. If I do that, it's not 60 CFM, it's 120 CFM. I'm doubling the quantity for half the time. Same. Everybody good? I have the option at 15 minutes on, 45 minutes off. When I do that, I quadruple the quantity. 240 in and then off during those other 45 minutes. Everybody good with that? All right. So in net, though, we're still 60 CFM, 24/7, 365. There's 3 types of ventilation. Negative pressure ventilation, balanced pressure ventilation, and positive pressure ventilation. Negative pressure ventilation is not recommended in the hot, humid South, and in Louisiana, we're not allowed to have negative pressure ventilation. Let's think about negative pressure ventilation. Let's call this a tight home, and we have 60 CFM being exhausted out of that house. Where did I get 60 CFM? If I'm exhausting it out of that tight house, where am I getting 60 CFM? Every penetration, every around those windows, around those doors, around those bathroom ventilators, around everything. Is everybody getting that? Well, here's the problem. If I'm sucking it in around that window casing, and this is, let's call it an open cell foam house, I'm going to take hot, dirty, humid air and run it along the side of that window or door casing right next to that open cell foam. What do you know about open cell foam and moisture? Like a sponge. So I am running moisture across a sponge. How often? Continuous. So that moisture is going to start to build up into that open cell foam until 3 years, 4 years, 5 years down the road, it is saturated enough to start now producing and mildews. Is that right? That is why we're not dealing with negative pressure ventilation inside these homes. If I added a fireplace, what's going to happen? Good, because you know that fireplace damper seals really, really good. Is that right? Good. Yes, sir, please.
We're having tons of sweating issues on these multi-stage systems. When we actually have a hot attic, we have less problems.
Good. We're gonna get right into that, and I'm so happy you're saying that. Man, you guys are just teeing it up for me here today. It's really great. Yes, and we will cover that in depth here today. Okay? Great. All right, so we are not allowed to use negative pressure ventilation. Gentlemen, let me ask you this. What is a kitchen hood? What is a dryer? What is a bathroom ventilator? Ah, okay, so all of these things are negative pressure ventilation, and that's what's happening in our deep south. We just made the air conditioner smaller. We're using all forms of negative pressure ventilation. And when we do that, huge amounts of humidity are being brought into the home with the air conditioner not being able to compensate. Is everybody getting that? Balanced pressure, exhaust fans are negative pressure. We're going to have to start controlling the moisture at its source. When do you typically turn on a bathroom ventilator?
And then they turn it off.
When you get out of the shower and it's filled with foam, I mean with fog, is when we typically start seeing that the fan gets turned on. Now, if it's filled with moisture, remember, heat travels from hot to cold, moisture travels from wet to dry. You have this whole room full of fog, and it's the master bathroom. What's adjacent to the master bathroom? Master bedroom. So if I have this fog and it's wet inside that master bathroom, where is that fog going to go? To the driest thing inside that room, which is the master bed, right? Sucking it into the sheets, sucking it into the mattresses, just sucking it all in there. When do you turn off that bathroom fan? When you leave, because mama slapped you on the wrist and turn off those fans, turn that stuff off. Gentlemen, we have to start making conversations, start having recommendations and saying, look, there are ventilation fans out there with humidity controls on there. As soon as you turn on that shower and the humidity starts hitting that, it's going to automatically come on and it's going to stay on until the humidity drops back down again. So you can leave the room and know that it's going to cycle back off. If they already have existing fans, the controls are able to replace the switches on most of those fans. So you can get humidity controls from there. You're not in the fan business, I get that. But you're in the moisture control business, and you have to be able to make suggestions. Is everybody getting that? Cool. All right. Stove hoods. 800, 1600 CFM exhaust hoods. If I had 1600 CFM, how many tons is that?
4.
Okay. It's 4 tons of air. But what I need you to get here is it's way more air conditioning than 4 tons. And that's what we want to show you here today. The greatest benefit that you're going to be able to provide is getting the makeup air that you're required, anything over 400, get that makeup air at the point of exhaust. The code has just changed. You're allowed to bring in makeup air from anywhere in that house that's connected to that kitchen and through ductwork. So what their thought process is bring it into the return, bring it into the duct system, and as long as that duct system continues and connects to this kitchen, you're allowed to do that. And up north, it's not an issue. But up north, they don't have humidity. We start dealing with a lot of this humidity in our market. We're going to kill the air conditioning system. Air conditioning systems in Arizona last about 25 years. How long do they last here? 4, just out of warranty, not even out of warranty, yeah. Yeah, so it's the moisture that's killing these units. You don't want to add another 1600 CFM of moisture to that air conditioning system. Is everybody good with that? What happens if I have an 80% furnace, I mean a 60 or 70% furnace, or I have a standard water heater inside that house and that home goes negative?
Combustion barrier.
What's going to happen, guys?
Sucks it in.
That's what's going to happen, is that right? And here's where you're going to see it. Because right up here at the top or right up down here at the bottom, there's usually rollout switches. So as it starts bringing that hot gas back down, that rollout switch trips, right? That limit trips and shuts down the water heater. The plumber goes back out there and he resets it or he replaces it, right? He does that 2 or 3 times under warranty, is that right? Then what happens after that? You know what happens after that. What happened? He unplugs it. He bypasses it, right? Because it's just a nuisance trip. The whole time we're sucking carbon monoxide back into that home. And it was fine as long as it was grandma's home. But now we're in a tighter home. In the tighter home, where does that carbon monoxide go? Over and over and over again. Is everybody getting that? You're going to start seeing people get sick. And I'm out there like Chicken Little screaming this out there. And I'm saying the sky is going to fall, the sky is going to fall. You guys please understand the sky is getting ready to fall. You don't want your customer to be that customer. All right? So balance pressure. Balance pressure are those ERVs or HRVs. What we're going to do on an HRV is take cool air. HRVs are used up north. ERVs are typically used farther down south. HRV, I'm going to take cold air from outside, run it through a heat exchanger, and bring it inside. I'm going to take the warm air from inside, run it side by side through that heat exchanger, and exhaust it outside, same quantities. So if I'm bringing in 50 and sending out 70, I'm going to heat up that 50-degree air to maybe 60 degrees coming in. Is everybody good with that? It's strictly sensible temperature. Strictly temperature on an HRV. An ERV is the same thing, except it has an enthalpy heat exchanger. Let's call it very porous heat exchanger. Moisture travels from wet to dry. So if I'm bringing in wet air from outside, and I'm sending out dry air from inside, that wet air is going to wick its way through that heat exchanger to the dry air, and I'm going to, instead of bringing all that moisture in, send some out. Now the problem with that is the efficiencies. HRVs are typically in that 60–70% efficiency range. When you start reading on the ERVs for down in our marketplace, you see that same 60 or 70. But they're rating it under the HRV, only during that mode, on the sensible side. You have to read down deep into their literature to find out what the efficiency is on the ERV side, and it's typically about 28, 27, 30% efficient. When you start seeing that, the amount of money that you're putting in to be able to remove a little bit of moisture that's coming in just far outweighs the effects of an ERV. So that brings us down to positive pressure ventilation. Positive pressure ventilation, we've been getting away with positive pressure ventilation using this particular product. It's an electronic control that we can override. It ties into a duct tied to the return from outside. So we have an electronic damper that we can use for override. That's that control that we talked about. We have a mechanical damper that we can adjust to get that 60, 80, 90 CFM. And it's tied to the return air. The problem with this is, when does that blower cycle off? When does your blower cycle off if we're satisfying code? Never. It's continuous. It's continuous. So how's that working out for your customer? Probably not so much. Is that right? Good. So if it's going to be on continuous anyway, why do they have an electronic damper here? Well, because these are set up to ASHRAE standards. ASHRAE 62.2 2010 is what they're setting this up. So what they're saying is, anytime it starts getting humid outside, this shuts down. Anytime it starts getting hot outside, this shuts down. Anytime it starts getting cold outside, this shuts down. When is this going to be open in Louisiana?
2 days out of the year.
Good. So Grandpa gets air 2 days out of the year. You understand what I'm saying? And possibly when the damper, when the blower is running, but maybe, but not necessarily. You follow me what I'm doing here? We're saying Grandpa's going to sit inside that ice chest, and he may or may not get ventilation air for the vast majority of the year. Where did that mold and mildew get its moisture from? Outside or inside that ice chest? It was the inside that we were concerned about. We needed to leave that gap at the top, and a certain amount in there, not just some. So the next thing that we can do is not turn on that air handler. Let's get something that has its own blower. If we do something like that, we can use the Braun FIN 180P. This is it, and it's been running this entire class, and it's blowing out that 60 CFM, or actually 90 CFM of air right now, so that's what you're hearing. Running well, it's taking care of that. But what am I doing? I'm taking that air from outside. I'm not running it into my air handler where I'm having wet air coming into the back of that air handler mixing with that cold air here. I'm running it into the plenum. When I run it into the plenum, when does this blower shut off? Never. 24/7, 365. It's code. Yes, sir?
Wouldn't that increase moisture in the supply?
Boy, nothing slips past you guys. I'm telling you, y'all are awesome. Yes, sir, it does. Yes, sir, it does. It will start increasing that moisture inside that home. Because right now, the only thing that removes moisture is what? My air conditioning system, is that right? And when is that running? A lot less, because now we have a tighter home, right? And we have a smaller air conditioning system. So this can satisfy the code. The code says this doesn't shut off, right? The 180p that we've installed here for you, or have running here for you, has the ability to run as code where it never cycles off. Or it's got the comfort condition available as well. I can flip it to comfort, and now it's going to go back to those ASHRAE standards where it's going to cycle on and off when it gets hot and cold outside. So it's going to decide when Grandpa needs to get some air outside in his ice chest. Not the greatest setup. Not the greatest setup at all. And I don't want you guys to ever make that change. If the customer wants to make that change, that's their business. Your job is to be able to provide code, which means this shuts off when? Never. Never. I don't want you to make that change, because then you have made that engineering side. All right? It just ties in. I'm going to tell you, make sure you insulate it, because in our marketplace, it's going to condensate. Okay? So here's that selection. When you go from the code to the comfort, you have these settings inside there. It's just a little dial inside here. You're welcome to look at that at break. There's the ASHRAE 2016, which is about twice as much as the ASHRAE 2012. And again, these are standards. And then number 3 is the actual code. The code is the IMC 2012-2015. When does it shut off if I'm on selection number 3? Never. So then what you can do is say, okay, well, I want it on comfort. I don't want it to bring in all this humidity all the time. You are allowed to go to zone 2A, which is where we are right here. You find zone 2A, and you are able to turn it to switch A or switch B. You're allowed to shift it to that. When you do that, what's going to end up happening is we're going to have the amount of air. See, that's that 1, 2, 3. We're having it in here, and then you can switch it to A or B if you wanted comfort. You have 2 speed settings, 130 or 180. At 180, if I needed that 90 CFM, 180, I'm going to put it on 50% of the time. 50% of that 180, I'm going to get that 90 CFM. Is everybody getting that? So we'll select it that way. Now, if I do go into the comfort mode, and I go to A or B, with no thermostat calling for it because we have it separate from our air conditioning system, anytime my dew point gets above 73 in A or above 75 in B, it's going to shut down. How often is your dew point above 73 or 75 in this marketplace? All the time. And I get that. So that's what I'm telling you. 90% of the time, Grandpa's not getting any air in there. What's going to start happening inside that box? Grandpa's going to get moldy, is that right? Absolutely. We're going to see some issues there. So understand what this is capable of doing. We're selling a lot of this out there in that Texas market now because they wanted to find something that satisfied the code but still was able to be changed. And I need you to understand what that means. That continuous means all the time. And they say, well, Rick, it says that it's ASHRAE 2010. That's fine. ASHRAE 2010 is a standard. It's not the code. The code is what you guys have to follow. All right, so here's where we're going to take a break. I need you guys to come back here in about 7 minutes. 7.5 minutes takes to smoke a cigarette. So get out, get back in here. Let's get this thing cranked back up. We're going to get into these psychrometric sheets, and I want you guys to be fresh. All right? See y'all in a few. We are in a huge wet market. How many of you guys have psychrometers? How many of you actually take them out of the truck? Okay. We are in a huge wet market. We have to understand psychrometrics because thermostats are not showing us what we need. We're thinking, oh, we got the dry bulb temperature, we got relative humidity. You're going to find out here today that that is definitely not the only thing that you're going to be trying to take care of. So a psychrometer, guys, just a basic psychrometer handheld is way better than not having anything at all. It's 60, 70 bucks. Please get one and start understanding the wet side of this business, because that's where the problem's going to start coming into play. I was just talking to the young man back there, and I said the biggest problems you guys are going to start facing as young technicians coming into this business is that the moisture is going to be the bigger part of what you guys are going to have to be dealing with. So let's get into the geek stuff a little bit. Let's get into this psychrometrics a little bit. What can we identify with psychrometrics? Well, dry bulb temperature, that's something we've been dealing with for years. We kind of understand that, but we need to understand its limitations. Dry bulb temperature, if it's 90 degrees in Phoenix and 90 degrees in New Orleans, where's it hotter? Because there's some other heat in there besides the dry bulb temperature that we're feeling, is that right? And what is that heat? Moisture, humidity, absolutely. So it doesn't tell you the total quantity of heat, it only tells you the level of heat. So 90 degrees in Louisiana, it's a lot harder to cool off than that 90 degrees in Phoenix. Your air conditioning system typically has a 75-25 ST ratio. 75% cools temperature. 25% of that system removes moisture. So typically, as it's running, it's doing a 75-25 sensible latent ratio. So it used to be 70-30 back when I was younger. I was your age, it was a 70-30. So it removed 70% sensible and 30% latent. Well, what happened there I was pulling out 3-ton systems and putting in new 3-ton systems, and the customers were saying, it doesn't cool like my old one. What they were really saying was it doesn't dehumidify like my old one. But the only thing they ever saw was the temperature on the thermostat, and they knew that they had to run it down colder in order to be able to feel more comfortable. Does that make sense? So if it wasn't dehumidifying as well, and we start moving into better and better units or 2-stage, multi-stage pieces of equipment, we need to start figuring out that sensible latent ratio. What's it really doing? So we're going to show you how to do that here today. But right now, your dry bulb temperature is just a level of heat, but not the total picture of how much heat's in the air. Wet bulb temperature. Wet bulb temperature is the minimum temperature which may be achieved by a purely evaporative cooling of a water-wetted ventilated surface. It's no wonder we don't understand what wet bulb is. Look, guys, I just need, you got to be careful with that. What I need you to do is blow on your finger. That's dry bulb temperature. Lick your finger and blow on it again. Was it cooler? That's wet bulb temperature. That's the temperature at which that water is evaporating off of your finger and into this air. The drier this air is, the faster it evaporates off. So the lower my dew point, my wet bulb temperature. Is everybody getting that? If my wet bulb temperature and my dry bulb temperature were exactly the same, that means the water's not evaporating off. Is that right? That must mean that this air is saturated, 100% relative humidity. So when my wet bulb and my dry bulb are the same temperature, it's a lot of moisture in the air. When my wet bulb and my dry bulb are really far apart, that means it's really dry in the air. Does everybody get that? Good. So wet bulb is my better indicator of the total heat that's in the air, the amount of moisture as well as the temperature. Wet bulb temperature, that's what we should be dealing with a lot more of. Enthalpy. Enthalpy is total heat. It's how many BTUs there are in the air. Does everything have heat in it?
Simply and not,
Yeah.
not waste out.
So we have heat in my return air, and I have heat in my supply air. Is everybody good with that? If I know how many BTUs there are in the heat going into my return, and I know how many BTUs there are in the heat coming out of my supply, I can tell you how many BTUs your air conditioner is actually removing. Does that make sense? Good. We're going to do that here today to find out how many BTUs you're bringing in with your ventilation air. Okay. Relative humidity. The amount of moisture in the air compared to how much moisture the air can hold at any given temperature. That's a stupid thing. Nobody really follows relative humidity because we think relative humidity is humidity. Two completely different things. If I had a 100-gallon bucket and I had 75 gallons of moisture in that bucket, how much moisture do I have relative to how much it can hold? 75%. So a 100-gallon bucket, 75 gallons of moisture, that would be similar to a 100-degree day, 75% relative. Everybody cool with that? What happens to the temperature at night? Drops down. So that means my bucket would get smaller. If my bucket dropped down to, let's call it a 75-gallon bucket, and I still had the same amount of moisture in the air, how much moisture do I have relative to how much it can hold? 100%. It's 100% relative. So if I drop down a half a degree, a quarter of a degree, an eighth of a degree, can the bucket hold the moisture anymore? No. We just reached dew point, and the bucket can't hold that moisture anymore. If I lowered that temperature enough, it's going to start running out as condensate. Does that make sense? Good. Where in my air conditioning system would I lower the temperature of the air enough to be able to wring out the air, get some moisture, and have it run out, let's call it a drain? Where would I do that? At my evaporator coil? Is everybody agreeing with that? At my evaporator coil, the water's going to lower the temperature, and we're going to run that water out down the drain. Is that making sense? So at your evaporator coil, gentlemen, what is your relative humidity at the evaporator coil? 100%. Everybody getting that? 100% right at the evaporator coil. Cool. All right. Grains of moisture. This is a better way of describing humidity. Because grains of moisture is, I like to think of it as gallons of moisture. Whatever God's sending in from the Gulf, when you get that southerly wind coming in from the Gulf, it's coming in and it's carrying all that moisture. And in Louisiana, we don't have grains of moisture. We have gallons of moisture pouring in, right? We have tons and tons of moisture coming in. So I like to think of grains of moisture and gallons of moisture being something the same. If I had an example of that, let's call it an 80-degree day, and they have 10% relative humidity. That means that there's only about 15 grains of moisture in the air. That same 80-degree day with 70% relative humidity, there's about 110 grains. So there's a lot more gallons of moisture in the air. Does that make sense to you guys? Okay. Dew point. This is that number I want you guys to get comfortable with. The temperature at which the air can't hold that moisture anymore, and it leaks out as a liquid. Can I reach dew point if I tore that insulation on that rubber tex? Yes? This is the audience participation part. You guys good? Good? All right. Can I reach dew point on that plenum? Can I reach dew point on the panel of that evaporator coil? Can I reach dew point just past that expansion valve? Good. Can I reach dew point on the drain line? Can I reach dew point just above that rust spot? We have reached dew point several times above the rust spot. So anything that's below the dew point temperature can sweat. Is everybody okay with that? It can condensate. I just have to lower the temperature below the dew point temperature, and it's going to sweat. The dew point temperature is the most important number that you're going to be needing as you start doing this business. If you don't have a psychrometer, You're just guessing. You're only checking the dry side of the system. You're not finding out what it's removing on the wet side. Here's your averages. This is throughout my Coburn's territory. Harahan, the high dew point temperatures from 6/1/17 to 9/1/17, the high dew point temperatures were 81 degrees. Your average in the Harahan market was 75. All right, do I have you guys any closer than that? No, let's go with that. So you guys are typically in that 81 degree high, 75 degree average. Average, every day, anything below 75 degrees is going to do what? Sweat. Ductwork? Absolutely, it's going to sweat. Absolutely. So here's your psychrometric chart. Stay with me up here first, and then I'm going to get you on your charts there on the table. So let's start off here on these charts. The dry bulb temperature, just what you're going to read on the thermostat, that's down here at the bottom. You'll see it's 20 degrees over here on this side and 120 degrees on this side. Anywhere along here, if I found 70 degrees, that would be my vertical line. That would be my dry bulb temperature. Is everybody okay with that? Everybody understand where dry bulb is? All right. The next one we're going to look at is wet bulb. Wet bulb is going to be the ones that go off at an angle this way. When they go off up at an angle this way, you're going to see 70 degree wet bulbs, 65 degree wet bulbs, 60, 55, 50 degree wet bulbs, and you would make a diagonal line. Everybody good with wet bulb? All right. The next one we're going to look at is enthalpy. I told you wet bulb was my best indicator of the total amount of heat. And enthalpy was total heat. Remember that one? Okay, so if I took my wet bulb number, let's call it 65 degree wet bulb, and I extended it out to my enthalpy line, it matches up with what? About 30? Does everybody see that? Good. So that's 30 BTUs for every pound of air. If I have a 65 degree wet bulb, I have 30 BTUs for every pound of air. Does everybody see that? Okay, good. That's enthalpy. The next one we're going to look at is relative humidity. Relative humidity are the curvy lines here. You'll see down here at the bottom one, that's 10%, 20%, 30, 40, 50, 60, 70, 80, 90. And this last curvy line right here is called our saturation line. It's 100% relative humidity. Everybody good? All right. The next one we're going to look at is our dew point. Now, on my chart up here, your dew point temperature is black. On your chart, it's black too, but everything else is black. So, on here, if you look at the dew point temperatures, you'll see 55, 60, 65, 70. Does everybody see that? That's where your dew point is. Directly to the left of that. Directly to the left of that is your grains of moisture. So if I have 65 degree dew point temperature, directly to the left of that is about 92 grains of moisture. Does everybody see that? So the more moisture we have in the air, the higher my dew point temperature is going to be. Everybody see that? Good. All right. All right. So what we're going to do is we're going to find out what's typical in somebody's house. If I take 75 degrees, because that's what you guys are designing your manual J's at for this marketplace, because that's what the state says you have to do. 75 degree indoor temperature. What's that happy relative humidity everybody wants to have?
40 to 50%.
Okay, 50%. So we're going to look at it. We're going to find 10, 20, 30, 40, 50%, and we're going to just draw a little line right there. So draw yourself a line at your 75 degree dry bulb and your 50% relative humidity. And Jody, if they're watching this on the video, then they can get the psychrometric chart at the Coburn's app or on the
App or online.
online at coburns.com. That's right, under the air conditioning section. All right, so everybody has that intersection, is that right? 75 degrees, 50% relative humidity. That intersection is what's happening in that house right now. So at that intersection, can I find out what my wet bulb temperature is inside that house right now? From the intersection, just draw a line at an angle right there. So my wet bulb temperature in that house is what, gentlemen? About 62, 62 and a half. Is everybody okay with something like that? Yes? All right. Can you tell me what my enthalpy is? If I extend that wet bulb all the way out to enthalpy, what's my enthalpy? 28. Good. About 28 BTUs for every pound of air. Everybody good? All right. What is my dew point temperature in this house? Find that intersection, go off to the right. 55. Everybody seeing about 55? 55, right?
Oh, that one.
Yeah, it's that's the line. There we go. Yeah, good. All right, so good. Everybody understands 55. That's the happy number I want you guys to keep in your head. 55-degree dew point. I would rather you know what the dew point is than the relative humidity. Because as you're going to see here later on, relative humidity is going to change. Dew point temperature of 55 tells you a certain level of moisture that's in that house, right? How many grains of moisture do I have in that house right now? About 65 grains of moisture. Is everybody seeing that? Good. So if I have this much moisture in the house, that's that number. If I told you what's a typical dew point temperature in the house, can you tell me? About 55-degree dew point temperature is a good number. Because we know that 75 degrees, 50% relative humidity, your dew point is 55 degrees. Is that right? Good. So, here's where it gets kicky. What's the temperature of the air coming out of your supply air ducts? 52, 54. We better start looking at that a little bit closer because we're going to have to pay attention to that. Because anything lower than 55-degree dew point is going to do what? Sweat. Ah. So if I'm running 56-degree air coming out of that duct and it's a 55-degree dew point, is it going to sweat in those grills? Not if it's 56 coming out and 55-degree dew point, it's not sweating, is it? But if it was 54-degree air coming out of there, is it going to sweat? Absolutely it will. Okay, so what about that grill that's by the door, by the front door? And the kids are in and out all summer long, right? Good. So it's 55-degree dew point in the house, but every time they start opening and closing that door, that 75, 81-degree dew point comes rushing in. Is that right? As that 81-degree dew point hits that 55-degree grill, what's happening in that grill? Sweating. Okay. That's interesting, gentlemen. I've got ductwork. And inside that ductwork is 55, 56-degree air. And the dew point outside is 80 degrees. 80-degree dew point. I'm going to run that 55-degree air through that ductwork, and it's going to start to thermal wash that insulation, which means it's going to go 55, 56, 57, 58, 60 degrees when it hits that vapor barrier. If it's 60 degrees when it hits that vapor barrier, what's going to happen if I have an 81-degree dew point temperature on the other side of it? It's going to sweat. We're going to have to change things, aren't we? We're going to have to change things up. All right. What I need you to understand is if this intersection was farther this way, I know it's going to be hotter in the house. If that intersection was farther this way, it's going to be colder in the house. If it's farther up this way, it's going to be wetter in the house. And if it's farther down this way, it's going to be drier in the house. So start understanding what this is doing for you and telling you if it's wet and hot or if it's cold and dry. We'll be able to figure out what's happening with that air in that home. I like to think of this as a big container. And if I just start pouring water in here, my grains of moisture increase. If my grains of moisture increase, what happens to my dew point temperature? It rises up. If I have this much moisture in here and I change the temperature, does it change the amount of moisture I have in here? Doesn't change the amount of moisture. The only way I can change the amount of moisture is to remove moisture or add moisture. Does everybody get that? Good. Good. Just by turning the air conditioner on or turning the heater on. How many times have you heard that? Oh, they turned the heater on and it dried out the house. All they did was raise the temperature in the house, but did it change the amount of moisture that was in that home? It didn't change the amount of moisture. The moisture stayed the same. And we're going to find out that relative humidity changes. All right? So, I have an 85-degree dry bulb temperature, and it's 75% relative humidity. Everybody good with that number? 85-degree dry bulb, 75% relative humidity. What if I raised the temperature to 110 degrees in a ventilated attic space? Would you expect my relative humidity to go up or down? Do you expect my relative humidity to go up or down or stay the same in a ventilated attic space?
Relative can go down.
Stay the same.
Stay the same. I heard go down. I heard go up. All right, good. So we got everything covered? Good. All right, so here's the deal. It's going to lower. It's going to go down. Because what we've done is we've just taken it from an 85-gallon bucket to a 110-gallon bucket. We still have the same amount of moisture in that attic space. Is that right? Good. So the moisture is the same. The temperature went up relative to what we had in that deal. Now it's only 35% relative. So I call you up. Man, you got to be here. It's 35% relative humidity here. What's going on in your head? It's dry, right? Oh my God, it's so dry over there. He's only got 35% relative. Oh my God. The first thing that you should be asking after somebody says what the relative humidity is at what temperature? At what temperature? Because as you change the temperature, relative changes, regardless of how much moisture you have. Is that right? Good. That's why I hate relative humidity. Still the same amount of humidity, just relative to the temperature it changed. Okay? Let's look at it on the psychrometric chart. If I had an 85 degrees, relative humidity we said was 73, so here's 73, and then I got a dew point out here at somewhere around 76 degrees. That's a normal temperature day, right, in somebody's attic space? Yeah? Must be first thing in the morning, right? 85 degrees. Okay. What happens if I raise that temperature to 110 degrees in that attic space? What happened to my relative humidity? 10, 20, 35% relative. Is everybody okay with that? Good. So the grains of moisture, the gallons of moisture in the air did not change. If we're only changing the temperature, relative humidity is going to shift around all over the place. Relative is a stupid number, and I really don't like it in our marketplace. Everybody good with this? Good, all right. That ductwork that's in the attic space, why does all of a sudden it start to sweat? Why did all of a sudden, over the last few years, that ductwork start to sweat inside that attic space? The dew point changed?
Yeah.
So God's been sitting in more moisture from the Gulf lately.
Probably.
More ventilation.
More ventilation to the attic. There we go. If I cool that attic off, back in the day, men were men, huh? It was 140-degree attic spaces. Man, you'd grab that screwdriver, you'd raise a blister off of it. I mean, you would just burn your hand on there, back if you had girly hands, because we all had just one big callus, right? Oh, yeah, that was back how it was. Yeah, so we had all of this 140-degree attic space. If the attic was 140 degrees, what was the temperature of your equipment? 140 degrees. It cooled down at night. We had ventilators on the roof, and we cooled it down, and we had the ventilator set at 110. Is that right? And that ventilator ran all night long, and that attic stayed 110. First thing in the morning, it's 110 in there. If it's 110 in the attic, what's the temperature of your equipment? 110. If the the dew point temperature is 76-degree dew point temperature, and your equipment is 110, is it going to sweat? No. So let's ventilate the attic. Let's cool that attic off. Let's make it as cool as you possibly can. Let's put soffit venting all around there. Let's put radiant barriers on the roof. Let's go ahead and put fans all over that house. Let's get that attic cool. So now, you wake up in the morning, your attic is 76 degrees. That means your equipment in the attic is 76 degrees. The unit comes on. Your dew point temperature is 76 degrees. Your unit comes on and starts cooling off that equipment, and how long does it take before it gets down below that dew point temperature? Not long at all. So we didn't change the dew point. We didn't change it with temperature. All we did was lower the equipment temperature in that attic space, right? Once the equipment temperature got below dew point, everything started sweating, and that all came from the radiant barriers and all the continuous soffits and all of that stuff that works great in Kansas City. But what are they lacking in Kansas City that we have an abundant supply of? Humidity, absolutely, absolutely. So then we say, okay, well, we're going to go ahead and run our equipment two-stage so that what? We can do what? Dehumidify inside the house, is that right? And that's a great thought process because we're in a humid market. We want to dehumidify. The problem with that is we were running 55-degree air through a duct. And how long do we want that two-stage piece of equipment to operate? As long as possible, right? So now we're thermal washing that insulation from that 55, 56, 57, 58 till we hit that 60 degrees. And then the dew point temperature is what? Higher than that. And what happens to the ductwork? Oh, so if I'm going to run two-stage, multi-stage pieces of equipment, I can't go with what this state says, oh, the minimum is an R6. Is that right? Good. So what would I have to do to be able to help prevent the thermal washing? We don't have any choice. They said the best place to put your ductwork is inside the thermal barrier. The worst place you can put your ductwork in a hot, humid market is in the attic space. Where do we put it? I mean, right there. That's exactly what we do. Absolutely. It's our fault we're doing this. So the best thing we can do is warm back up the attics. Well, wait a second. That is so counterintuitive to what we want to do as air conditioning contractors because we want the attic cooler so that it doesn't penetrate the house. Oh, my goodness. But as soon as we got it cooler, what did we do to the ductwork? We made it rain. That's right. So understanding the psychrometrics behind that is huge. Yes, sir, please.
With the cabinet, what would you call an attic? What's the limitation of what's too hot?
Well, I know 140 was pretty hot, and I never saw anything sweating in there. So I don't know what that number is. It's going to depend on if it's an 81-degree dew point day or a...
But to penetrate as the insulation barrier inside
it's not,
the cabinet?
It's not insulating, it's not penetrating that cabinet.
Okay.
Understand that. That 55 degrees inside is going to the metal.
Yeah.
Right? So what if you're in the dehumidification mode? What's the temperature of that air going through there now? Even colder.
Yeah.
So I'm running a colder evaporator coil, and it's going to go faster before it hits that metal. 50-degree air penetrating through there, now it's going to reach that dew point much quicker. But if I got that equipment hotter and kept it above that dew point, above that 81 degrees, oh, maybe that's the kick.
140 degrees would be incredible.
I'm going to tell you 110, but that's going to change too. So okay,
Yeah.
so be aware of that. All right, if it's at 73-degree dew point temperature outdoors, what would you expect the dew point temperature to be? Higher or lower in a well-ventilated attic space? Absolutely the same. Whatever moisture level you have outside, you're going to have the same moisture level inside. And we use the example of the screen door on a submarine, right? If I had a screen door on a submarine and I ran that submarine underwater, how much moisture am I going to have inside compared to outside? Exact same. So if I have an 80-degree dew point outside, what should I expect my dew point temperature to be inside? 80 degrees. If my ductwork gets below 80 degrees, it's going to... There it is, guys. There it is. Got to keep the ductwork warmer than the dew point temperature. So now I have to make the attics warmer, which is very contradictory to anything that any contractor is going to want to do. Yes, sir?
Are you developing the seat for store in the future? Are you developing the air conditioner seat for store in the future?
Come on, back when men were men, we didn't need no suits. It never affected me.
Yeah.
So how do you handle that in a foamed house?
So, in a foamed home, what's my dew point temperature in the attic space? So it's going to be 55 degrees, is that right? Or somewhere thereabouts. 55-degree dew point in the attic space, my ductwork has to get what temperature before it finally decides it's going to sweat? 55-ish, right? Right in there. Everybody good with that? So that's why it's more important to bring the ductwork into the conditioned space. That's why I tell you guys, quit putting your air handlers on a platform in that closet. Your return air temperature is at 73 degrees, and it's 55% relative. What would you expect the supply air relative humidity to be? Oh crap, he says, I love that.
Supply's going to be 100 right off the floor.
Ah. It's going to be near 95% relative humidity coming off your supply. But that gets so crazy to a technician because he's saying, wait a second, my air conditioner is a dehumidifier. I should have less humidity on my supply than my return. All we did was lower the temperature. And when I lowered the temperature at my evaporator coil, my relative humidity was what? 100%, because I was able to start getting it to reach dew point and run out. So if that temperature is 56 degrees, 55 at my coil, 56 degrees coming out of the supply, I raise the temperature just a hair, my relative humidity is going to start going down. Does that make sense to you? Good. So that's telling me at my supply air grill, it's 95% relative humidity. Have you ever seen the mud on the ceilings right there? Yeah. And they say, oh, that's coming out of your ductwork, right? They tell you that? Newton said for every action, there's going to be an equal and opposite reaction. So if I'm blowing air out, what does that mean going to that grill? Dust. So I'm taking dust from the floor and it's running straight up. That air is going out, this dust is coming up. As soon as I run dust up to 95% relative humidity. What do we call 100% relative humidity? Water or Coors Light, right? So I take that dust and run it right up to that ceiling. It hits that water and mud on the ceiling. It's not coming through your ductwork. It just came from the dirty floor. Very carefully.
Yeah, I was playing.
Huh? I just need you to understand. Typically, what I would have done, I'd have pulled the grill down and I'd stuck my hand way inside there and I'd pulled it out. And what would I have come up with? dry, and I'm sure it's probably going to be clean. In most cases, it's going to be very clean. Yeah? And then I can explain that to a customer. It's the dust that's in the house that's picking up. Good?
Same with the dope.
All right. So if I had that 73-degree dry bulb and 10, 20, 30, 40, 55% relative humidity, I had a dew point temperature in this house of about 56 degrees. Supply air temperature comes out at 56 degrees. I'm up at somewhere around 95% relative humidity. Is everybody getting that? Good. It blows a lot of technicians away, and I just need you guys to get a visual on this. So total heat. This is the number that I'm trying to show you, that if we get the total BTUs on a unit, we're going to be able to find out the total BTUs that we're bringing in with ventilation air. Enthalpy. Yes, sir. Yes, sir. So homeowner says, my unit's not keeping up. It doesn't feel like I wanted it to feel. Back in the day, we had our thermostat set at 78 degrees. And then it shifted down to 75 degrees. And then it became a 72 degrees. What's that happy number that everybody's talking about today?
68.
68 degrees. I'm hearing it all the time. Every class I teach, that's the same number I hear everywhere.
Now blame it on medical.
They blame it on the medical field, but we don't have that many people in the medical field. It's just a bunch of people that didn't go outside because Nintendo was invented. So we have this propensity to stay inside conditioned space now, and we feel like we need to be cooler and cooler. So we've run that temperature down. So here's what I want you to do. Find 60-degree wet bulb on your chart and draw a line all the way out to the enthalpy line on your 60-degree wet bulb. Go all the way out to the enthalpy line. What is your enthalpy at 60-degree wet bulb?
38.
60-degree wet bulb, you should see something about 26 and a half. Is everybody seeing that? There's 26 and a half BTUs for every pound of air in the return. Everybody good? Do I need to hold off a second? We're good? All right, we good? All right. Supply air temperature. We used our psychrometer, and we saw that we had a 50-degree wet bulb in the supply air. So find 50 and run that all the way out to your enthalpy line. So everybody sees somewhere around 20.3 or something very close to that. All right, so here's the gig. While your unit is running, you had 26 and a half BTUs for every pound of air in the return, and you have 20.3 BTUs for every pound in the supply. That means that air conditioning system removed 6.16 BTUs for every pound of air that ran through there. Everybody good with that so far? All right. So the formula is CFM times your HD, your heat difference, times 4.5, and that's going to be the total BTUs that system is removing. 4.5 is a constant that never goes away. And if you ever forget this formula, just plug in the two wet bulb temperatures into that calculator on the Coburn's chart, and we will be able to provide that information for you. Okay? So we have CFM times HD. We measured with a flow hood all of our CFM all the way throughout that house. And on this 3-ton system, we found out we had 1237 CFM times my 6.16 HD times that 4.5 that's a constant. That 3-ton system right now is removing 34,289 BTUs. How's it doing? Pretty good. Pretty good. All right? But she's not happy with that. Because you're going to now check the supply air and return air temperature, not just the wet bulb. And in that case, that same wet bulb, wet bulb that you had for supply and return, she has a 69-degree return air temperature. 69-degree return air temperature. Is the system working? Because she wants it at what? She wants it 68. And she's got a 69-degree return air temperature. The unit's not keeping up. She's aggravated. But you have to be able to prove capacity. So we're going to prove capacity. When we do this, you see that she's got an 18-degree temperature split. Everybody good with that? So we're going to plot this here. We just drew that 60 for my return, and I'm going to take my 69-degree dry bulb, and I'm going to draw a line straight up here. Everybody good with that? So right now, this intersection is my return air set point. Everybody good with that? Everybody know what I'm talking about? Okay. We're going to take our 50-degree wet bulb for our supply and draw that line out. And what's my supply air temperature? 51. Find 51 and draw a line straight up from there. Everybody good? I told you on this chart, this was what? This was our moisture, is that right? This was what? Temperature, right? Temperature and moisture. So watch this. Watch this. We're going to take a line from this point straight across. When you do that, this system is now removing this many BTUs. Yes? This is how much moisture it's removing, and this is how much temperature it's removing. So let's plot that. From that angle right here, from that angle, draw a line straight out. You're going to like this. What did that line go to on your enthalpy? 25, is that right? This is how much moisture it's removing. So from 26.5 to 25. What's the difference between 26.5 and 25? 1.5. Everybody good? 1.5 of my 6.16 total is moisture removal. So 1.5 divided by 6.16 is 24%. This system is removing 24% latent and 76% sensible. Is that cool? That's cool. Because now, what you guys are going to be able to do is start proving what your sensible and latent of that high efficiency equipment that you're buying. Because let's stop and think of it at a very simple level. A very simple level. If I had a two-stage unit, the compressor is typically 100% and 66%. Is that right? When it drops from high to low on the fan speed, it's 100% down to about 75%. So I'm running a 66% compressor and a 75% fan. Am I moving more air across that coil than I would have before? If I'm moving more air across that coil, what just happened to the coil temperature? It went up. If it went up, what do you think is going to happen to this sensible latent? I'm going to be removing a whole lot more sensible and a whole lot less latent. Is everybody getting that? So we have seen it. Jody and I did some checking, and we've seen conditions where it's 99% sensible and 1% latent on low stage. Is that contradictory to what they're telling us that's going on? And I don't know what your equipment's doing. I'm telling you, you're smart enough now to go check your equipment. And you decide whether your equipment is doing what it's supposed to be doing for you. Does that make sense? Okay. So why did we go through all of that? We went through that so that we can figure out how much moisture am I bringing in? How much heat am I bringing in with that 60 CFM from outside? Let's take a typical day in your market. Let's call it 95 degrees, 60% relative humidity. That means I have a dew point of 78.9. Is that a typical summer day in your marketplace? Not here? What's your typical dew point temperature here? Average. 75 was your average. And high was 81. Is that right? We're at 78.9. Is that a summer day? It's a summer day. So a 95-degree dry bulb, 79-degree dew point temperature, I can have that. Is that right? Good. What does she want inside the house? Let's call it 70 degrees, 10, 20, 30, 40, 50% relative humidity. Everybody good with that? This is your HD. This is your heat difference that you're bringing into that house. You had 46.5, 25.25. The difference between there is 21.25. Everybody follow that so far? My HD is 21.25. I told you that if I drew a line this way and this way, and then ran that up at an angle this way, I could tell you that this was what? Latent, moisture, and this was sensible. 21.25 times my 4.5 times my 60 CFM, I am bringing in 5,700 BTUs. How much is that? 5,700 BTUs. Half a ton, right? If it was just a half a ton. Half a ton, but when we ran this angle out here, we have now figured out that I have 14.75 here divided by the 21.25. 70% of what I'm bringing in is latent heat. You guys getting that? 30% of what I'm bringing in is sensible heat. So I'm bringing in a lot of what? Moisture. Your air conditioning system removes 75% sensible and 25% latent, and I'm bringing in 70% latent and 30% sensible. Does anybody see a train wreck waiting to happen? Because when does that ventilator shut off? It's continuous. By code, it says it's continuous. Absolutely. So, we are bringing in a lot of moisture here. And remember that other house, that bigger house, that 4,000 square foot home? We said how much air did that one need? This one needed 60, the other one needed 90. Okay, so 90 would be the same. That house is next door, so it's the same outdoor conditions. They still want the same 70 indoor. So the conditions are going to be exactly the same, except it's going to be 90 CFM. What are they bringing into their house? 8,600 BTUs. Watch this. 8,600 BTUs total times your 70% latent means I am bringing in 6,000 BTUs of latent. That's a half a ton of latent air. Your air conditioning system removes 3/4 sensible, 1/4 latent. If I have 1/2 ton of latent coming in, how much air conditioning do I need to compensate? Half a ton of latent, I'll need 1 ton, 1.5 ton, 2 tons to be able to compensate for that. Does everybody get that? I have a half a ton of latent that I'm bringing in. And that system can remove 75% sensible, 25% latent. I need 2 tons to be able to remove that. So as that blower is running, I need to be able to remove 2 tons. I have to add 2 tons of air. What? Didn't we just make the air conditioner smaller? We just made it smaller. We're not going to be able to remove that moisture. Is everybody getting that? All right. Good. All right. So it's going to take a 2-ton system to compensate for that 60 CFM of ventilation air just because of the latent heat. Not so much just because of air that we're bringing in. Sensible heat's easy to remove. It's that latent that's hard for that air conditioner to remove. So I need to add 2 tons. Man, that's just incredible. But let's take it one step further. We said that we have a lot of pieces that are in that house that do negative pressure ventilation. And when they start exhausting stuff, we have to bring in hot, dirty, humid air. Let's call it a dryer. If that dryer turns on, when does it shut off? It doesn't, okay? So that dryer is going to move 200 CFM if it's just a standard dryer. You start getting into the big boy dryers, it's going to be up into 300 CFM. That's twice as much as your house used to breathe. 200 CFM times your HD times your 4.5, I'm bringing in 19,000 BTUs being sucked into that house. 70% of that is going to be latent in our particular case. That's 13,000 BTUs of latent because of the dryer. If I have 1 ton of latent, and my system removes 25% latent, 75% sensible, how much air conditioning do I need to compensate for just the dryer? That's 1 ton of latent. 2 tons, 3 tons, 4 tons. Is everybody getting that? Your dryer alone running brings in enough latent that you would require a 4-ton system to compensate just for your dryer. You get that? But I told you, make up the air at the point of exhaust. Remember I told you that? Make up the air at the point of exhaust. We said that about the kitchen hood. So if I have a laundry room and it's sucking out 200 CFM of air, I want to be able to put a makeup air at the point of exhaust. So put in a barometric damper into an exterior wall right there. So anytime that laundry room starts sucking that air out, the barometric damper opens up. It might be a spring-loaded damper. It opens up, it starts bringing that air in from outside. So now you're just bringing air in from outside and right back out. It's not taking it from the rest of the house. Take the door to the laundry room, close it, and put a threshold down at the very bottom of it. You don't want to suck all that from underneath the door because you've defeated the purpose. Does that make sense? Is that laundry room going to get hot? Yep, it sure will. But what's that going to do to the rest of the house? I don't need that 4 tons of air anymore. Does that make sense? Good. But it's a conversation you need to have with the homeowner prior to. By getting that?
Because aren't you still taking conditioned air out of what's being dumped out of the house from what's being dumped in that laundry room?
It is, but it's not making it positive or negative. I'm trying to keep that going. Yes, 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 sir, please.
On a gas dryer, it's going to be worse every time you even take more air out.
I lost my combustion air as well. Does that make sense? Yes. Yes, absolutely. So I need to be able to have a bigger barometric on that. Absolutely. Good. All right, so we're talking about the dryer at 200. Let's talk about a kitchen hood at 1,000. The kitchen hood at 1,000, I'm going to be sucking in from every crack and crevice, 95,000 BTUs times my 70%. 1,000 CFM exhaust, I'm bringing in 66,000 BTUs of latent. That's 5 tons of latent. How many tons of air conditioning do I need to compensate for that hood running 1 hour? 20 tons, 5 tons, 10 tons, 15 tons, 20 tons. I need 20 tons of air conditioning to compensate for that. I'm telling you guys that you really, really want to make sure that any of that air that's coming in through that makeup air is right there in that same room with that exhaust. The code says you can bring it in somewhere else now, but I'm going to tell you. Jody, all right? Good. All right. So it's going to take a 2-ton system to compensate for that 60 CFM of ventilation air just because of the latent heat. Not so much just because of air that we're bringing in. Sensible heat's easy to remove. It's that latent that's hard for that air conditioner to remove. So I need to add 2 tons. Man, that's just incredible. But let's take it one step further. We said that we have a lot of pieces that are in that house that do negative pressure ventilation. And when they start exhausting stuff, we have to bring in hot, dirty, humid air. Let's call it a dryer. If that dryer turns on, when does it shut off? It doesn't, okay? So that dryer is going to move 200 CFM if it's just a standard dryer. You start getting into the big boy dryers, it's going to be up into 300 CFM. That's twice as much as your house used to breathe. 200 CFM times your HD times your 4.5, I'm bringing in 19,000 BTUs being sucked into that house. 70% of that is going to be latent in our particular case. That's 13,000 BTUs of latent because of the dryer. If I have 1 ton of latent, and my system removes 25% latent, 75% sensible, how much air conditioning do I need to compensate for just the dryer? That's 1 ton of latent. 2 tons, 3 tons, 4 tons. Is everybody getting that? Your dryer alone running brings in enough latent that you would require a 4-ton system to compensate just for your dryer. You get that? But I told you, make up the air at the point of exhaust. Remember I told you that? Make up the air at the point of exhaust. We said that about the kitchen hood. So if I have a laundry room and it's sucking out 200 CFM of air, I want to be able to put a makeup air at the point of exhaust. So put in a barometric damper into an exterior wall right there. So anytime that that laundry room starts sucking that air out, the barometric damper opens up. It might be a spring-loaded damper. It opens up, it starts bringing that air in from outside. So now you're just bringing air in from outside and right back out. It's not taking it from the rest of the house. Take the door to the laundry room, close it, and put a threshold down at the very bottom of it. You don't want to suck all that from underneath the door because you've defeated the purpose. Does that make sense? Is that laundry room going to get hot? Yep, it sure will. But what's that going to do to the rest of the house? I don't need that 4 tons of air anymore. Does that make sense? Good. But it's a conversation you need to have with the homeowner prior to. Are you getting that?
Because aren't you still taking conditioned air out of what's being dumped out of the house from what's being dumped in that laundry room?
It is, but it's not making it positive or negative. I'm trying to keep that going. Yes, 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 sir, please.
On a gas dryer, it's going to be worse every time you can take more air out.
I lost my combustion air as well. Does that make sense? Yes. Yes, absolutely. So I need to be able to have a bigger barometric on that. Absolutely. Good. All right, so we're talking about the dryer at 200. Let's talk about a kitchen hood at 1,000. The kitchen hood at 1,000, I'm going to be sucking in from every crack and crevice, 95,000 BTUs times my 70%. 1,000 CFM exhaust, I'm bringing in 66,000 BTUs of latent. That's 5 tons of latent. How many tons of air conditioning do I need to compensate for that hood running 1 hour? 20 tons. 5 tons, 10 tons, 15 tons, 20 tons. I need 20 tons of air conditioning to compensate for that. I'm telling you guys that you really, really want to make sure that any of that air that's coming in through that makeup air is right there in that same room with that exhaust. The code says you can bring it in somewhere else now, but I'm going to tell you, in your marketplace, you want to go beyond the code. All right? You want to be able to put it in right there at that hood. And explain to the customer what's bringing in. You're going to have these conversations going, okay? So you said, Rick, you took the hottest day of the year. Man, we never hit those days. We only hit 4 of those days a year. Okay, watch this. Watch what's happening here. Let's call it a shoulder season day. Let's call it a 75-degree day outside. 75 degrees, 70-degree wet bulb temperature. And she still wants 70 degrees inside the house. 50% relative humidity. This is a typical shoulder season day. Is your ventilator still running today?
Yes.
We're going to take this and run it down and run it across. We're going to take this and run it out at an angle. When I do this, your enthalpy difference is 8.75, latent difference is 86%. Gentlemen, 7.5 here out of the 8.6, 87% of what we're bringing in is latent. It's what? Water. We're bringing in 90% water with this thing running. When does it shut off? It doesn't. If I'm bringing in this on a day that's 75 degrees, how much is your air conditioning system running? It's cycling on and off based on sensible temperature, is that right? It's on that dry bulb. I'm bringing in tons and tons of water, and it's not seeing it as heat. It's cycling on and off very, very sparingly. Everybody getting this? If there was only something that I could bring in that fresh air from outside and not have the air conditioner run, but still be able to remove the moisture. God, what would we call that? Dehumidifier. Guys, that's exactly right. If I take a dehumidifier, bring the air in from outside, run it into the dehumidifier. I will still take air from inside the house, run it into the dehumidifier. Blow that into the supply plenum. Now listen to me. Your dehumidifier is going to produce some heat. There's the heat of compression from your compressor, and there's the heat of the fan motor in there running too. You'll typically see about a 10-degree temperature rise from the return to the supply. So if I have this just blowing in the house, it's going to be about 80 degrees blowing into that house. Somebody's going to get real upset. So you blow it into the plenum space so that it can mix with some of that other air. Is everybody getting that? Good. So if I'm getting it mixed with that other air, now it's going to come out a little bit less. But I want you to pay attention to where you tie it onto that plenum. Because you're moving about 300 CFM into a 1600 CFM plenum, that air is going to do whoo and just start slowing down. And it's going to find the easiest path to get out. And that's going to be the biggest duct. The biggest duct is the kitchen, it's the living room, it's the master bedrooms. And you don't want that heat going out there. So you want to go ahead and move it as far away from the big ducts as you possibly can before you introduce it onto that plenum. Does that make sense? Cool. All right, I think that's a great place. If you have a cathedral ceiling, where is the wettest spot in that entire house? The top of that cathedral. So you take that supply duct and you take that and you stick it right there at the top of that cathedral and you blow it straight across there, because I'm going to take that and mix up that moisture so I can get it to change states and mix back into the house. Is everybody getting that? If you have that huge stairwell in that foyer up front and it goes up 30 feet up there, you know what I'm talking about? Where's your cloud of moisture? Up there. Dump that back into there.
Do you want it all in that space, or do you want to split it?
I can split it. I can divide it up a lot of different places, but I want to get that moisture off of that spot. Does that make sense? Get that moisture off of that spot. Get that air turning. Because when does this cycle off? Never. I want to get that air turning all the time so that I can get that moisture back into the house, back into the dehumidifier. Everybody good? Good. So obviously if I put it in here, it's going to come here, it's going to work its way back to the return. And when is this blower going to cycle off? But the compressor is going to cycle on and off based on the humidity inside the space. Is that right? So when it gets wet inside here, it'll cycle back on and off. That works out great. Now guys, if it's a foam encapsulated home, if the whole attic is here's what I'm going to tell you. Don't put it into the supply plenum. Have your supply blow up into the attic space. Where's the wettest spot in that attic? Right here. If I take this air and put it back into the supply plenum, I am going to condition this. If I blow this up here, I'm going to continually change over. The University of Austin did a study called the Ping-Pong Effect, which means that the moisture rose up like a cloud, right? That's what it does. It gets sucked into the open cell foam. When it does that, the heat from the sun hits this, it forces that moisture back in, and it rises up. It gets up a little bit higher. Then it keeps going, until it all settles in here, and then you start getting rotting happening up here. What I'm telling you to do is blow this up here, keep that air moving, changing over on a regular basis. We don't get that stagnated air up here, and we can get that air moving back down into the space. Is everybody getting that?
So you're saying in that instance, don't run that into the plenum?
Exactly.
Okay.
Does that make sense?
Yes, sir.
Good. Because then your attic becomes positive. Your whole ceiling, we want it to be Swiss cheese. I want those can lights that are not insulated in a foam house. I want that. Because now that air, because it's positive, is going to force its way back through there and then back down into the space. And I'm going to turn this over. What's going to be the temperature in the attic space compared to the house? Virtually the same. What's going to be the relative humidity in the attic space compared to the house? Virtually the same. Is that making sense? So, the building scientists are saying this. In the South, a tight, well-insulated house is more likely to have problems with higher indoor humidity than older, leaky houses. We said that. As soon as you close that ice chest, it gets nasty inside, right? Air conditioning runtime is reduced, especially during the shoulder season, so we don't dehumidify. Less time to run means that dehumidify the interior is less. Adding mechanical ventilation only makes the situation worse. Two researchers, these two guys, if you're going to read up on any indoor air quality, these are the guys you want to pay attention to. And that's Max Sherman and Ian Walker. And they wrote, the use of an ERV did not change the humidity distribution in a hot, humid climate compared to continuous exhaust systems. Now they're saying negative pressure ventilation. And the ERV didn't even do better than that. What do you think? What do you think it's telling you? Man, don't use an ERV. It's not going to do anything that you're trying to make it work. The solution to this problem is not an ERV. The solution is a standalone dehumidifier. Now, Department of Energy says this. There was a consensus that nationally, the ventilation rate is significant enough to warrant a separate whole home dehumidification. Nationally. What does that mean for you guys down here in the Deep South? Yeah. There's very little argument that we want to be able to see that 40 to 50% dehumidification or that relative humidity. But that relative humidity is 50%, but it's not just 50. I told you 50% is relative. Don't necessarily go with that number. 50% at what temperature is what I told you to ask me. 50% is at 75%, so at 75 degrees. So when you read it on the internet, and they're saying 50%, they're meaning at 75 degrees. So 50% at 75 degrees gives me a dew point temperature of what? Does anybody remember? What was my happy dew point number that I told you? 55 degree dew point temperature. So that's the level of moisture that's in that house. But we also said Miss Homeowner doesn't want 75 degrees in her house. What does she want? 68 degrees. 68 degrees means my relative humidity is what? 10, 20, 30, 40, 50, 63%. So that same level of moisture in the house, because she dropped the temperature from 75 to 68, is now running 63% relative humidity. So she's going to call you up and say, oh, this thing's not working. It's 63% relative humidity in my house. And your next question is, at what temperature? Because right now, 63% is fine. It's fine. Because our dew point temperature is still that 55-degree dew point temperature. That's what we're shooting for in our marketplace. How much moisture do you have in the house? Does that make sense? If she doesn't call you, what's she going to do to the thermostat? She's going to drop it down. And when she drops it down, now what's going to happen to my relative humidity? Go up. Here's what I need you to understand now. Now it's 65 degrees in the house. I have sheetrock right there. What do I have on the other side of the sheetrock? Insulation. I have insulation on the other side. I have a 76-degree dew point temperature in the attic space. I have insulation, and I have sheetrock. 65 degrees in here, 76-degree dew point on the other side. What's going to happen in that wall? Good. Because remember, insulation doesn't stop moisture. Tyvek, the moisture retarders, stop the moisture. If you don't understand that, take a handful of insulation, stand it up, take a hot pot of coffee and set it on the top. Do you feel any heat? No, because it's insulated. Is that making sense? Pour it. What just happened? Because the moisture runs right through insulation. The moisture travels right through. The thermal stays there. What's coming through that wall right there is moisture. And you saw the sheetrock doesn't do any good. Is that right? So that moisture is all the way up there. You'll see that there's a lot of insulation out there that's installed backwards. They've got the paper, the craft paper, right up against the sheetrock. Is that right? If I have sheetrock and then paper for my moisture barrier and then my insulation, I have moisture going all the way through my insulation, all the way to the paper. Is that right? I have 76-degree dew point still right at the paper, and now I have 65 degrees on the other side of the paper. It's going to condense inside there. We need to have our vapor retarder on the outside edge in the deep south. You'll see as you move farther north, their vapor barriers on the inside because they want to stop the moisture from leaving. They want to keep the moisture in the house. We want to keep the moisture from getting in the house. The vapor retarder changes. Is everybody good with that? Sweet. Notice those second floor units. When they have that second floor and all the walls of that second floor are in the attic space, is that right? And you've seen the insulation put on the side of it. Where's the Tyvek?
On the inside.
There's no Tyvek at all up there, is there? No, they didn't put Tyvek. They didn't put a vapor barrier. They just got the insulation stuck in the side of that. What's happening upstairs? Wet to dry, is that right? It's pouring through there. And you're wondering why you can't get that upstairs dry.
Especially about outlets. Every day is coming around outlets.
Everybody getting that?
Having that problem in a commercial building, we actually bring to make it. You don't want to.
So you did some radiant barriers. Okay. So remember, guys, as the temperature goes down, relative humidity goes up. But it's relative. The moisture stays the same. So high relative humidities, guys, as we start getting up there above our 55-degree dew point temperature, because that's that number we really want to pay attention to, your bacteria start growing, viruses, funguses, molds, mites, respiratory infections, ozone production, all of that starts picking up. Anybody remember FEMA trailers? Yeah. We took this All of these things that are filled with VOCs, we put these cans in the hot, humid market. They off-gas faster in hot and humid, and we didn't bring in any ventilation air. So you just stuck Grandpa in that ice chest and you just walked away. You follow? It got ugly fast. Dust mites. Anything above 50% relative humidity, dust mites thrive. They live. They like it. Dust mites eat your dead skin that flakes off, and whatever goes in must come out. That's right. So it's been reported that after 2 years of pillow usage, 33% of the weight of that pillow is dead dust mites and fecal matter. He says, absolutely. So that's 2 years of pillow usage. How long has he had Scooby? Okay, so you're understanding when the allergists say, oh, take away the stuffed animals, this is exactly what we're trying to do. Or we need to be able to keep it below 50% relative, because if I can keep it below that, dust mites can't live. They dry up, shrivel up, die, they're gone. So we need to be able to produce. Where was that shower? I mean, where was that steam going? Oh, right into that master bedroom. Remember that? Yeah, so that bed stays wet all the time. What do you think you're sleeping with? Mm-hmm. It's not the only ugly thing you're sleeping with. There it is. All right. So guys, dehumidification. I want you guys to start thinking it through. When you start seeing a 98 pinter, there's 8 pints in every gallon. Is that right? 8 pints in a gallon. That's 12.25 gallons of water a day that can remove. If you look at our weather, we're somewhere about 2,400 cooling hours a year. We have a 9-month cooling season. So if you average all that out on a 4-ton system, we'll remove about 11.25 gallons a day. A 95 will take out 12.25 gallons a day. Yes, sir.
Can you oversize one of those in a house?
Can you oversize one in a house? Yes. If I put in a 120-pint dehumidifier in a 2-ton house, what's it going to be putting out of the supply side? Heat. If I put in that much heat into a 2-ton house, the air conditioner is not going to keep up. Does that make sense? So that would be the downside. It's not going to be that it's going to over-dehumidify. It's just going to be that you're putting in too much heat into that house. Okay? All right. So you're going to be looking at the model number and finding out the 98 pint. Remember, there's some formulas out there that are asking for pounds. 1 pint, 1 pound. There's 8 pints in a gallon. There's about 8 pounds in a gallon. So just know that you can interchange those numbers. Compare products out there. What you want to start paying attention to is you're looking for a high efficiency dehumidifier. High efficiency is going to be down here on the efficiency. How many pints per kilowatt will that dehumidifier remove? So in this case, that 70 pinter will remove about 5 pints per kilowatt. The 98, 6.1 pints for every kilowatt. More efficient. Is that right? Good. Then we go from the 98 to the 105. When I shift to the 98 to the 105, it's virtually the same amount of moisture that it'll take out. Is that right? But it's going to remove 8.8 pints for every kilowatt that we use. And you're paying about 10 cents a kilowatt. This is going to take out almost a gallon for every 10 cents of runtime. Does that make sense? Good. There's other ones out there. The 155 is a high efficiency as well. And then the 205. They're good pieces out there. But if you're going to start looking at how do I do this? If a house had a 5-ton unit and then they foamed it, right? Now it's oversized. What do I have to do? Put in a dehumidifier. Because if you put in the dehumidifier in there, what is the whole reason we're sizing our air conditioning right? Is so that it gets enough run time to dehumidify. Is that right? What if I have something else removing the humidity? This could just toggle on and off. Is that right? It's just handling sensible. This is going to take care of all the moisture. So you want to get the most efficient dehumidifier because it's going to be running a lot. Everybody getting that? Good. So start looking into the efficiency. The 105 is a great, great tool. Something new out there right now. This is called the MD33. It's a self-contained unit. It's about 6 inches deep, and it sits between the studs. So I can take this whole piece, just stick it in between the studs of a second story. All your controls are inside, the fan's inside, the compressor's inside, your thermostat's in, your humidistats inside. So everything is self-contained for this. This is great for those, you know, the 2 bedrooms upstairs with the bathroom? The kids leave, they're turning that thermostat up, and it's really getting mold and mildew up there. Great for that one. This is a great one for that frog. You guys know the frog? That friggin' room over the garage? You know the one I'm talking about? This is great for the frog. It's able to dehumidify that section without having to make sure that air conditioner is running enough to cool up there. This is great for camps. What do they do at camps in order to be able to keep them dehumidified? They got to run the AC, is that right? Here's an ability to be able to put in something that they can run the dehumidifier and not necessarily run the air conditioner during that time. Does that make sense? Good. This is a great piece out there, and I wanted you guys to be aware of it. How many pints does it remove? 33 pints, right? It's a great piece. They say up to about 1,200 square feet. That's 1,200 square feet in Kansas. Probably about 800 down here in our marketplace. Good. All right. Here's the other thing I wanted you guys to be aware of. Split system dehumidifiers. We now have a split system dehumidifier. This is going to take care of about 4,000 square feet. 184 pints a day. That's a lot of water. What's nice about this is now the condenser's outside, what's it not blowing in the house? Heat. It actually produces 4,000 BTUs of sensible cooling in the house. So about a 1/3 ton of cooling takes place with this particular piece. It's really a nice item. It's for your high-end homes or your light commercial units out there, split system dehumidifiers. We went with Ultra Air because they're a family with Santa Fe. Santa Fe is that group that does all of the swimming pools and all of those kind of things, Thermostor. So they're able to provide engineers to help us with those specialty projects that we're needing. Understand that's why we've gone to this particular product. So guys, look at the job over time too. If you're not looking at psychrometrics, you're not looking at the whole picture. This is a THL2. This is a data logger. I plug it into my computer. I say, I'm going to Mrs. Jones's house. I want you to check it every hour, and I want to leave you there for 5 days. I get to Mrs. Jones's house, and I press go. Right off the bat, it's going to give me a a dew point temperature, a dry bulb temperature, and a relative humidity temperature. And every hour after that, as long as I leave it there, it's going to record this information. I come back, I plug it into my computer, and it gives me this information. This air conditioning contractor was getting sued because the air conditioner didn't keep up. Foam constructed home. We took this, we put it in the attic space. Homeowners left for a week. When we got there, the dew point temperature was 56 degrees. How's that doing? Good. The temperature in that attic space was 77 degrees. How's that doing? 77 degree attic space? The relative humidity was about 45%. But over time, once we left that house, we saw that it went up to 85 degrees, 86 degrees. The next day it got up to 85 degrees in the house again. The next day, up in the attic space, it was 95 degrees in that attic space. Typically, it's going to be about 5 degrees warmer than the house. Is that right? Good. Next day, it went up to 94 degrees. It's getting hot in there. Is that right? But watch this. Every time the temperature went up, what else went up? The moisture. The moisture level. Watch. Every time it went up, it went up. Every time it went up, it went up. When it went down that little bit, it went down. It followed. Because heat goes from hot to cold, moisture goes from wet to dry. I was getting heat and moisture from somewhere. And that could either be from in the house or from outside the house. Homeowners left. There was no dishwashers going. There was no showers going. There was nothing going. So where do you think we got that heat and moisture from? This was all coming in through the foam, through a bad foam job. We took a thermal imager, turned on the thermal imager, and just started looking around in the attic space. And there was nothing but holes everywhere, heat pouring in. And if heat was coming in, what else is coming in with it? Moisture. Thermal imager. You guys really need to have it. Guys, if you're using a thermal imager with foam, you can't see where the heat's coming in until you use your thermal imager. And then all of a sudden you're seeing where all the heat is everywhere in that house. And we're seeing bad foam jobs everywhere. So please, please be careful and go look. It looks great like this.
Yeah.
But it's not so great when you look at it like this. So use a thermal imager, get something out there to protect yourself. Because if I see heat coming in, what else is coming in? Moisture.
Shouldn't the foam guys have them too?
Oh, wait a second.
They're not going to do that.
They're already cutting their jobs.
Should they? That's a big question. Should they? Yes, they should.
Probably 90% plus of foam jobs never get thermal imaged after they're done.
Well, I can promise you they're not. But you guys are counting on a certain amount of R value on that foam, because that's what you sized your equipment for. If you're not verifying it, nobody's verifying it. I'm telling you, yep, time to get into the thermal business, because now you're not guilty until proven innocent. I mean, you're not innocent until proven guilty. You're guilty until proven innocent. Is that right?
Most of the problems we're finding with foam is the pockets between the roof line and the foam itself.
That's it.
They get an air pocket, and as the foam starts to dry, it opens this pocket.
There it is.
And your moisture develops right there, and then you get this rot through.
We're seeing holes over the patio, because you know they'll foam up over that, and then they have to go out there and run a ceiling fan out there. So they cut a big hole in the foam to go out over that, and now you just have a huge open window into your conditioned space. Is that right?
I did.
So again, thermal imaging, guys, you got to get into thermal imaging, because that's going to tell you where the moisture is coming in. All right? Look, it has the standalone, but it also has the one that fits onto your phones. So I know a lot of the younger guys like their phones, and that works out nice. This is the Pro version. We're not selling the homeowner version. All we're selling is the Pro version. The Pro version has more pixels. Every pixel gives you a sharper image of the temperature, because every pixel is a temperature color. What the Pro version also has that the homeowner version does not have is the big complaint was you always have to pop off the your case in order to be able to make this thing fit. On the Pro version, they have a dial on the back of it, and that makes it pop right on up again. All right. I know. Get your minds out of the gutter right there. Okay. So you got your dial. So that's going to pop up there and make that happen. Android version versus iOS. You do have that capability. All right? So just to give you an idea of what the difference is. And I love my C2, my FLIR C2. I love it because it gives me a good picture. But getting the difference between what we're selling with the C2 to what we're dealing with now with the Reveal Pro, it's huge amounts of difference. Look at the wheels on the train. You kind of figure out that around and around. So you can kind of see what it is, but here it's very, very clear on what we're dealing with. So again, it's the number of pixels that we have available. Guys, if the indoor air is polluted and you could see it, this is what your jobs might be looking like. But you know, remember, we have to ventilate. Dilution is a solution for the indoor pollution. If we're not bringing in that ventilation air, or if we're bringing it in less than what it's telling me that I have to have, you're closing that lid on Grandpa in there. You getting it? You're telling me, okay, Grandpa, you only need it when the air conditioner's running. You know, we have to have it when? How long? Continuous. Thank you very, very much. I hope you all learned something from the class. I hope you enjoyed it. If there's something I can ever do for you, HVAC@coburns.com will reach Jody and I, either one of us, so don't hesitate. I'd like to see this. This is going to end up on that the HVAC@coburns.com, and it's going to end up on our Coburn's Connect app. Please go take a look at it and see if that, that helps you out anything, okay? Good. Thank you all very, very much. I hope you enjoyed it.